Hello everybody. In this video we are going to look at the solutions to the honors electromagnetic induction homework problems 6 through 10. Let's get started. Problem 6. The magnetic flux through a coil of wire containing two loops changes from negative 50.0 Weber to positive 38.0 Weber in 0.42 seconds. What is the EMF induced in the coil? What are we given in this problem? Well, we are given the number of loops or the number of turns in the coil, which is 2. We are given the initial value for the magnetic flux. And remember, for magnetic flux, we are going to use the Greek letter phi, or some people say phi. And that is at negative 50.0 Weber. We are given the final value for the magnetic flux of 38.0 Weber. And we are given the time it takes to go from its initial to its final value of 0.42 seconds. We are being asked to find the induced EMF in the coil. And remember, we use the Greek letter epsilon for induced electromotive force. To solve this problem, we need to use Faraday's law. And Faraday's law tells us that the induced EMF is equal to the negative of the number of turns of loops, or the number of loops in the wire, times the change in the magnetic flux divided by the time. No need to do any rearranging for this problem. I just plug my known values into the equation, and just be careful that we know that oops, let me use the pen here for this. Sorry about that. Let's use the pen. That the change in the magnetic flux is going to equal my final minus my initial value. And because my initial value is negative 50 Weber, I have a negative, I'm subtracting a negative, which means that I'm adding. So you just have to watch out for that. And when I do that, I will come out with a value of negative 420 volts. Problem 7. A single 9.6 centimeter diameter circular loop of wire is in a 1.10 Tesla magnetic field. The loop is removed from the field in 0.15 seconds. What is the average induced EMF? The diameter of my loop of wire, and I know that it is a circular loop of wire, and that'll come in handy in a few moments, but the diameter of my loop of wire is 9.6 centimeters. I know I'm going to need to know the radius because it's a circle, so the radius is the diameter divided by 2. That's going to give me 4.8 centimeters for the radius, which I know I need to convert to meters, so that will be 0.048 meters. The number of turns is 1 because I'm told that it is a single loop of wire, so that means my value for n is 1. The magnitude of my magnetic field is 1.10 Tesla, and I know the loop is removed from the field in 0.15 seconds. So that is kind of a key word right there. It's removed from the field. So when the loop of wire is in the magnetic field, it's going to induce an EMF. As it's moved out of the field, it's going to go from whatever that value whatever that magnetic flux is to a flux of 0 once it is out of the magnetic field. So it's going to go from a maximum to a minimum value. And they want us to know what the induced EMF is. So we're solving for epsilon. We're going to use Faraday's law once again, and this time I'm solving for my induced EMF, so I don't need to do any rearranging for the problem. And I know according to Faraday's law that my induced EMF is equal to the number of turns times the change in the magnetic flux divided by the time. I know that my change in the magnetic flux is equal to the area times the change in the magnetic field. So I know that I can then replace delta phi with A times delta B. And I know that my area is equal to 2 pi r. I'm sorry, not 2 pi r, that's circumference. It's pi r squared. So I can replace the area with pi r squared. Now I can calculate the area separately before I get into Faraday's law, and then just plug my area in. That way is fine too. It'll come out right either way, and you'll see me do it both ways when I go through these problems. But once I have this equation, I can then plug in my known values. And when I do that, I'm going to get an induced EMF of 5.3 times 10 to the minus second volts. Problem 8. A single 10.2 centimeter diameter coil is initially oriented so that its plane is perpendicular to a magnetic field of 0.63 Tesla pointing up. During the course of 0.15 seconds, the field is changed to one of 0.25 Tesla pointing down. What is the average induced EMF in the coil? So again, my number of turns is going to be 1 because I have a single loop of wire. My diameter is 10.2 centimeters. And once again, I know I'm going to need to find the radius. So the radius is going to be half of the diameter, and that is 5.1 centimeters. And when I convert that to meters, I will have a radius of 0.051 meters. The initial value for my magnetic field is 0.63 Tesla, and when it is at that value, it is pointing up, and we are going to say that up is our positive direction. After the course of 0.15 seconds, the field is changed to one of 0.25 Tesla, but now it is pointing down. So now that it is pointing down, my final value for the magnetic field is going to be 0.25 Tesla, but negative 0.25 Tesla because it is pointing downward, or in the opposite direction it was at its initial value. And it makes that change from a positive 0.63 Tesla to negative 0.25 Tesla in 0.15 seconds. Once again, we are looking for the induced EMF. And once again, we chose up as our positive direction, so we are going to use Faraday's law to find our induced EMF. Again, no need to rearrange for our unknown. We're already solved for induced EMF. The only thing I have to do, as I did in the previous problem, is swap out the area for pi r squared. And when I plug in my known values, I'm going to get an induced EMF of 4.8 times 10 to the minus second volts. Problem 9. A 15 centimeter diameter circular loop of wire is placed in a 0.50 Tesla magnetic field. When the plane of the loop is perpendicular to the field lines, what is the magnetic flux through the loop? Once again, we are given the diameter of the loop, which is 15 centimeters. The radius is going to be half of that. So my radius will be 7.5 centimeters, which will equal 0.075 meters. The magnitude of my magnetic field is 0.50 Tesla. And we are being asked to find the magnetic flux, or phi. I know that the magnetic flux is equal to the magnetic field times the area, or phi equals B times A. And I know my area is pi r squared. So I plug my known values into that equation, and I will get a magnetic flux of 8.8 times 10 to the minus third Weber. Problem number 10. The magnetic field perpendicular to a circular loop 12.0 centimeters in diameter is changed from positive 0.52 Tesla to negative 0.45 Tesla in 180 milliseconds, where positive means that the field points away from an observer and negative toward the observer. Calculate the induced EMF. In this problem, we are given the number of turns. It doesn't say it explicitly, but you'll notice that we have a circular wire loop. They're using the singular tense, so we can assume that there is one loop. The diameter of the loop is 12 centimeters. Once again, to find the radius, we just divide the diameter by 2 and then convert to meters. So we will have a radius of 0.0600 meters. The initial value for my magnetic field is positive 0.52 Tesla. And my final value for the magnetic field is at negative 0.45 Tesla. And the time it takes to go from its initial to its final value is 180 milliseconds, which when converted to seconds will be 0.18 seconds. And they're asking us to find the induced EMF. So we're solving for EMF. This part here where they are telling us where positive and negative means, they're just giving us our frame of reference, really isn't important to the problem, and they are actually defining their z-axis the opposite way that we do. I guess that's perfectly fine. Everybody's free to make their own decisions. I don't think whoever wrote this problem, I don't think I'm going to invite them to any of my physics parties, but other than that, it's their choice, so that's okay. Let's take a look at the solution. We're solving for induced EMF. So using Faraday's law, we don't need to rearrange the formula. We're already solved for our unknown. Again, as I have before, I have to take my area and substitute pi r squared for the area. I plug my values into the equation, and I am going to get a EMF of 6.1 times 10 to the minus second volts. We just have to be careful that we're watching our signs here. Remember, my final value was negative and my initial value is positive. So I have a negative minus a positive. So you just have to be careful of those signs when you're plugging them into the equation.